There we go. Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on Twitch right before all of our very eyes. We are in the middle of doing sort of our own renderer, which is kind of awesome. We're basically implementing essentially what a GPU does. We are implementing that ourselves so that we can see how it all works. And I think one of the things that's been kind of surprising is it really hasn't taken us very long. Like, you know, kind of was thinking in the back of my head, like, oh, we're going to have to implement this whole render. You know, I mean, I hadn't done much in the way of software rasterizing in a long time. And I was kind of like, wow, all right, that's going to be a major undertaking. It turns out, like, we just kind of blew through a bunch of it. And it was like, you know, a couple days and we had all of the sort of primitive stuff working, and it was just weird. So I hope it continues to go that way. It was a little surprising, but that's how it is. So we're going to go ahead and continue with that today. Before I begin, let me remind everyone that we are on day 95 today. So if you are someone who has pre-ordered the game at handmadehero.org and you would like to download the source code so that you'll be where I am today, get that from the link that you got in your email and unpack day 94 source code into a directory. That is what I am starting with today, and so you will be right with me if you would like to be. Now, where we left off, we just did a brief aside yesterday on gamma correction at the behest of Wanshun. And so basically what we did is we added some gamma correction to our little texture mapping routine, which allows us to draw little rotated and scaled versions of any of our sprites that we want to. And so, you know, we kind of wrapped that up to some degree. Now, someone was asking on the pre-stream a little bit, and I haven't read, they were referring to something that they posted on the forums, which I haven't had a chance to read yet. I will absolutely read it. I pretty much read everything on there. You know, sometimes it takes me till the weekend to have time to do so, but I always go through it all. And they were asking about how the gamma interacts with premultiplied alpha. And if you take a look at the way that we were doing things, right, where we did our sRGB to linear stuff, sRGB to linear, sRGB 255 to linear. If you took a look at the way we were doing stuff, right, what we were doing is we were kind of lofting our values up, and we were doing all of our math and making sure that we did all of our math in sRGB 255 space and all this sorts of stuff. But there's one thing that we didn't talk about, and it's a good thing to mention, which is that if you are doing premultiplied alpha, then you kind of have this problem of when exactly do you premultiply the alpha, right? Because this sRGB to linear thing, it seems like you probably want to premultiply the alpha. You know, you want to make sure that when you do your alpha premultiplication, you're doing that. Presumably, you want to do that in a linear space, right? So that you have already converted things out of sRGB. When you're doing your alpha premultiply, you do the premultiply, then you do the blend, and then you know, et cetera, et cetera. So it's kind of one of those things where I believe, and we didn't meticulously inspect this, but I believe we're essentially doing what I would consider to be the most correct thing right here, I believe. And it would be nice to have a real rendering authority take a look at this and verify that that's correct, because I'm certainly not that guy, but I believe we're basically doing it as correct as you might possibly be able to do it. But when we kind of move past what we're doing right now and try to optimize this a little bit, one of the things that often comes up is how do you deal with storing your alpha values? How do you deal with storing your color values so that you can store them already pre-multiplied? You know, do you pre-multiply first and then convert? You know, do you pre-multiply in linear space and then store sRGB and whatever? And the reason for that is, you know, maybe we don't want to have to do the alpha pre-multiplication in here and so on and so forth. So there's a bunch of issues in there, and I'd rather just tackle those when we get to them, because right now I believe we're doing things correctly where, you know, I have to think about it, but basically what we're doing right is we're sampling from a texture which is not pre-multiplied alpha. So it's got the actual sRGB values in there and the actual alpha value that was used in Photoshop. We're converting out to linear, right? We are then blending in, you know, non-pre-multiplied space linearly, right? And then we are doing the alpha composite after the fact. Now, The problem, I guess now that I think about it, the problem with that is this bilinear blend might actually want to be in premultiplied alpha, right? Because I think the bilinear blend, like we were talking about before, when you're doing the lerps, doing lerps want to have the alpha premultiplied into them already. And so if we wanted to make this a little more correct, I suspect what we would want to do is take the alpha out of these guys and premultiply it in right here after the gamma correction, if that makes sense. So it would be something along the lines of, you know, for each of these texels, because we've kind of got it over. Let's see where we're doing that here. Let's see. So when we load this in, we've got color A times color R times texel R. Unless we just, oh, okay, is it this right here? RSA. No, so this is, did we remove something? So this might not be correct. We may have forgotten something yesterday, because now that I'm starting to go through it with a fine-tooth comb here, I'm looking at this. Where are we actually doing our alpha multiply, right? Because I don't see it. Texel dot A. I don't see our multiply, right? So I think it's missing. Do you guys feel the same way? I feel like we had it in here and I removed it accidentally when we were doing this. I feel like it should be multiplied in here, right? And let's take a look. Let's see about the change in appearance that we get from this. Let me make our little. We do have a little bit of an issue with our our tree being crazy psychedelic right now, which is not going to be conducive for us testing some stuff and debugging. So let's put a little bit of a let's calm down, if you will, this sort of trippy psychedelic thing that's happening here with our tree, so that we can concentrate on just what's happening with the actual renderer. That seems like probably a good idea, to say the least. So okay. So if we take a look at what's going on there, we'll see if we can perceive any difference here as well. Because again, this will only really be in the edges for the most part. So let's take a look. So if I come in here and I say, all right, at the very least, we're not doing the premultiply properly, so we want you know, our colors to be premultiplied here. Let me just see what happens there. So there we go. That would be if we actually multiplied in the alpha. Now it's almost impossible to really see any difference there. And again, this is why I say a lot of times, unfortunately, a lot of this stuff is kind of more about the theoretical correctness than actually seeing artifacts on the screen, because sometimes it's almost impossible to actually perceive that difference. But yeah, so yeah, can I see that? Not really. Yeah, that's just not something you can really see. I know, and if I can't see it, you guys definitely can't see it, because it's going to be kind of blurred out on the stream. So yeah, I would say first of all, I feel like our texels are not premultiplied properly here, because we are not storing them premultiplied, was my understanding. Now maybe I'm wrong about that. Let's go. Let me go look to see. Maybe we did actually do that. Like I said, it's been a long time. So maybe in our loaded bitmap routine, we are storing them premultiplied already, in which case that is where that's coming from. So debug load bitmap. Are we premultiplying the alpha in here, right? Okay, so we are. So that's the answer. The answer is that we are storing these guys premultiplied already, and that's where that goes. So yeah, if you think about what's happening there, then we are not doing the most correct thing, right? Because what happens here, and at least, again, most correct thing, I'm just saying this from my own personal opinion of the read on it. You know, like I said, you'd probably want to ask more of a rendering expert. But what's happening here is we're turning our texels from sRGB to linear, but they've already been premultiplied by the alpha out here, right? And so technically we're not, at the edges where we have partial alpha, we're not actually getting back the correct sRGB values because we're getting back the sRGB values after they've already been premultiplied. And they were premultiplied in sRGB space, which isn't necessarily what we want, right? And so one way that we could sort of look at handling this, right, if we want it to be more correct, what we could do here is we could say, all right, let's not do that. So when we load our bitmaps, let's not premultiply the alpha at all, right? Let's not do that. So if I do that, now obviously we're going to ruin everything else on the screen that's being blit, certainly. So that's a little bit of a problem. But here we go. Let's restart that. So everything but our tree will be wrong, which is, not the best thing. But now, in this case, when we are loading our bitmaps, they are correctly not premultiplied, right? And if they're not premultiplied, then what I was saying now becomes the correct thing to do, which is to say that when we do these and we load them and convert them into linear space, then we can do our alpha multiply. So that's basically going to be like the RGB of the guy is going to be multiplied times the A, right? We convert all these guys from premultiplied, from non-premultiplied to premultiplied. So convert to premultiplied alpha here. Then the blend will happen correctly because we are in premultiplied space, which is where we want to do the blend. So that happens properly. And then we can do, I believe, the rest of this the way that we would want to do it. Now, we do have, I guess, one other problem, which is thinking about it when we output. We're going to want to output our alpha, our color values want to be not premultiplied at this point. So we've got kind of a little more work to do there, but I believe that would actually be the correct thing to be doing there if I'm not very much in error, which I might actually be. But I think that's correct. Now again, it's really, you just can't see the difference to a lot of these things. There really isn't any thing to see there. But I believe that would be more correct, right? Because now we're converting from sRGB to linear, then we're premultiplying, then we're doing the lerp, then we're doing the blend, and that is, I believe, actually correct. Now, the only thing that I was saying that we aren't quite thinking about yet is what happens on repeated blends. So if I'm, kind of repeatedly blending to the screen, like when we were producing our ground chunks, for example, where there's lots of splats that are layered on top of each other, I have to think about what happens there, because I don't know. I don't think there's anything in particular we have to be concerned about with that. It seems like it'd be correct, but the final ground splat, I guess it doesn't really have, the final ground splat doesn't really have any transparent parts. But if the final ground splat had transparent parts, one of the problems that I think we would have, right, is the RGB values in it are, we were outputting them as if the whole thing was premultiplied. So that means that the values are actually premultiplied by the alpha, which is not what we would have wanted to have happen, right? So we'd have to kind of think about that, right? We'd have to kind of think through what that actually means. So it seems like you're kind of in this nasty situation where you really want your stuff to all be premultiplied alpha, because you'd constantly be fighting this thing of like storing, incrementally storing to the premultiplied alpha. I don't know. Let's think it through on the blackboard, because to be honest with you, I don't even know really what the correct answer there would be, right? Because that's pretty complicated, and you don't actually do this in hardware. You typically store the things already premultiplied. That's just how that works. All right, so let's think about this. If we were going to do this, right, then we've got sRGB in a buffer, right? And we've got A. So those are coming in, and I don't know what we'll call this. We'll call this color and alpha or something like that, right? So this is what comes from the artist, yeah? Now, we know that we can do everything properly here if we do it in light linear space, which we've already talked about. That's what we talked about yesterday. So what we want to do is grab this C value, right? And we want to take the C value and turn it into linear, right? So we can do that by, let's say this is C in sRGB, so then we have a C in linear space, right? So the C in linear space, we can now do anything we want with, but we already know that our alpha values don't actually work properly if we use lerp, right, without premultiplying them. So we need to premultiply it if we want to go through the lerp function, right? So in order to do that, what we'd have to do is we'd have to do CL times A, right? And we would then have that to work against, you know, some destination. So we would be producing CL times A, and then eventually we would be writing that, you know, into a buffer, right? And that buffer now actually would have effectively pre-multiplied alpha in the buffer, right? So if we wanted to then use it in the same context as one of these artist supplied ones, we pretty much would have to multiply by the inverse of the alpha value in order to restore this, right? I mean, because we're producing this, because in order to go through lerp, we have to do that. So if we wanted to put it back into this format, right, there's really not much we could do about that. Like, you know, we don't really have the option, I don't think, of doing anything else there, right? And that's a dicey proposition, because multiplying by the inverse of the alpha could be 0, right? And so 1 over 0, right, is not a value that you want to start having in your code, because then you have to like special case it and do all sorts of things. So I feel like we just probably don't want to go this route, right? We want to store our values pre-multiplied if we can. So what we could potentially do, I have to think about this, but what we could do is say, well, what we want to have happen here is we maybe want to have the linear value from our colors, right? We want to say, if we were to take the value as linear, then multiply by the alpha, then project it back to sRGB, we'd store that value so that when we pull it out, it's linear again, right? It's the right thing. It's A times C linear, right? Instead of A times CS projected to linear, right? So we could, you know, if you believe what I just said there, which, you know, like I said, I'm not really a rendering guy, so I don't like to state these things very authoritatively. Maybe, you know, we can only go by what we can determine on the whiteboard. And like I said, a lot of these things, it's hard to see the artifacts, so we can't really guide, we can't really use what it looks like as a guide. We'd have to start thinking about it more mathematically, and actually maybe we could write some little tests that would draw things and test the values that come out versus some things we think should happen, you know, that sort of thing. But we can't really make much in the way of decisions about whether it's important for the game, because they really just always look the same at some level. So what we could do is say, all right, let's store the pre-multiplied alpha values, but instead of storing them the way we were, where we multiplied by the alpha value, maybe what we do here is we do this sort of lofting where we do the sRGB to linear in here, right? So we say, all right, let's go ahead and read in whatever the bitmaps texel value is there, right? Let's go ahead and read that in like we were reading in the other stuff, and where we've got you know, our red at the top, our green, like so, and our blue here, like so, and alpha. Let's read that in. And then let's loft it up just like we were doing before. So, you know, take that texel and turn it into, you know, a texel that's linear, right? And once we do that, then maybe we say, all right, at that point, we take the texel and we multiply the texel's RGB, right, by its A. So we do the pre-multiplication for alpha. And then before we store it, we project it right on back. Right? We do the linear one to sRGB 255 in there. And then when we store it, we're storing a value that we know when we pull out the value again, it's going to give us the correct pre-multiplied value in that linear space, right? Hopefully that makes some sense. I don't know if that made sense to you guys. but hopefully that makes some sense. And then we kill this premultiplied alpha here because we just assume that they're always in premultiplied alpha all the time anyway, right? RGB is not a member. What? Serious? Are you serious? Well, you know, it's true. It's not a member. Well, let's fix that, I guess. So here's our union. So I guess what we'd do is we'd say, all right, let's go ahead and have an RGB and a real A in there, like so, I guess. Although, well, this A and this A will collide. So I guess technically, if we're pushing it a little bit here, we'd do this, right? It's a little gross, it's true, but there we go. So yeah, so that, when we load now, we should probably verify I did a bunch of stuff there, but that when we load now, well, it doesn't look like that quite did what I was hoping. That looks like the background there is still. So I guess the other thing that I have to think about there is what that. Yeah. So now that I think about it, that's fine for our routines that are actually gamma aware, but our routines that aren't gamma aware are going to cause a problem now, right? Because they don't actually do the conversion back afterwards. So, you know, this is now going to be a value that produces a blend that's kind of a little bit unusual, right? So we'd have to go and modify our other routines to be aware of that, which is fine because we're all going to switch to doing all this stuff through that main path anyway. So I suppose that's fine. We could just say, all right, in our draw bitmap call that we have, this one right here, we could do that conversion, that handling as well, right? That's not that big of a deal. All we would really have to do is say, all right, when we load the sRGBs here, we could just upconvert them, right? So yeah, so let's do that. That's not that huge of a deal, right? And that way we'll at least be uniform in both paths. I guess the other thing we could do is just ignore it for now and until we actually have everything going through draw bitmap slowly, which I guess is the other thing we could do. I think I'm going to just port it for now. I think that's the easier thing to do so we don't have to get too ahead of ourselves. So yeah, so all right, what we would, excuse me, what we would need to do here is we'd need to, again, load the texels just the way that we had been doing it before, right? So we've got all of these guys here, and that C alpha is going to have to happen down here somewhere, right? So texel RGB is going to have to multiply by C alpha outside there now. So if I go ahead and take this guy here, right? And I've got all of these guys, real 32, oops, didn't mean to do that. Real 32, like so. So there I got my R, my G, my B, and the A value here, this. So I've got all those in the texel. I do the sRGB to linear of that texel, as always. So we grab the texel out, we do the sRGB to linear, we multiply by the alpha, and we produce also the texel.a here. We don't need to do that divide by 255 because that's already baked into this guy now. And when we compute this, we got to multiply the RSA by the C alpha as well, so that's fine. We then go ahead and read out that destination. The destination we would also like to upconvert, right? Because we said we're doing the frame buffer that way. So our dest, our dest here, whatever we'll call that, D, that's going to be another one of these reads. Off we go. And there's our alpha, goes at the end. So there's RGB and A. So the RGB and A values, grab those out. We can then convert that texel as well. So D equals sRGB to linear D. So then we can do everything like we were going to do with the blend. We have checked that math for errors. Of course, we're changing the math now. Then we compute what we would actually want to do in terms of putting it back. And in this case, what we really want to do is actually just make this be sort of what we're going to write. So this is our result, right? And our result is going to be all these values. I'm going to put them in a vector so I can unmap them. There's our inv. So there we go. Oops, got my equals. And so that should do it, right? And then we can just take result and do linear to sRGB on it before writing it out. And I think that converts that routine, if I haven't made some egregious errors in there, into something that will actually, oh, right, got to actually use the values that we said we were going to use. There's the texel red, oops, texel red, texel green, texel blue, and the RSA, RDA, those sorts of guys are all good. What is the problem here? Oh, that's not dest, it's D. RDA is undeclared. RDA in this case is just the destination A, right? It doesn't have anything special happening to it. RSA is that reversed RSA there. I'm sorry, RSA is just the compounded one. And then RDA, what did I do there? RSA, okay, that was a typo, sorry. RSA, so this should be DA, and this should be DA, and RSA stays what it was. So when we are doing this, we multiply all of these guys out. So technically RSA, we can just actually do the full multiply here, right? Because these are both being multiplied by the same thing. So we can actually just say texel multiplied by C alpha, and then RSA, right, is just the same value. RSA is just texel.a, right? So I think that should pretty much do it. And does that jive with what we were doing up here as well? I guess we are still doing it here for no apparent reason. Yeah, no apparent reason whatsoever. And so really we can collapse these two to do the same stuff. And again, they will be the same eventually. We'll probably have all this stuff collapsed down anyway. But for the time being, I guess we will kind of avoid doing that. So inv RSA we'll leave. RDA we'll get rid of. We'll just make this des.a, and we'll make this des.a. And then that RSA is, again, just going to be texel.a, like so. And so texel.a now needs to actually have this done to it, but so does this color A happen to have to do the multiplication there. So we're just going to do, again, that exact same thing. So texel times equals texel.a, right? I'm sorry, color.a. There we go. So yeah, I believe that does the same thing on both paths, right? Here we've got that C alpha, right? Looks about right. The RSA has to be color.a now. RSA has to be color.a. I'm sorry, texel.a. That was a mistake there. Texel.a. Yeah. So let's see. Let's see how that's looking, whether that's a total nightmare or not. We should probably stop generating the ground. Oh dear. Well, it did not go well. We can say that. Obviously, we're not quite... You gotta love it when you get a full blank screen, right? You just tweak a few things and all of a sudden you've got an entirely blank screen to contend with. Oh, okay. No, we're good. Never mind. It's just because now everything's so much slower because we have this ridiculously slow path. It just takes forever to draw all the ground chunks. So that's fine. Yeah. No big deal. And so now you can see we've restored everything back. Our compositing of the background looks proper. And our tree is still our tree. Nothing particularly weird happening there. Yeah, So all right, I think we're getting a little closer just in terms of stuff, but now we're super slow because all of our stuff is really, really slow. And so, you know, one thing we probably should have to start thinking about at this point is how we're going to make sure our software renderer runs relatively quickly. Now, of course, at this point, it may actually be true that we, excuse me, that if we actually asked for compiling with optimizations on, we would get a pretty good boost here because we're not actually asking for that at all. So let me see. I've got -OD there. Let me switch it to O2 and see what the difference is. Because now we've actually got routines that it matters how fast they run. Wow, what a difference that is. Look at how fast that runs with optimizations on, right? Versus how fast it runs with optimizations off. Okay, that was on. Here's off. Like it's incredibly slower. And that's just because we're actually doing a bunch of intensive code there. And so if the optimizer actually, you know, does some even just basic things to it, it probably makes a huge difference. I mean, look at this. It's not even up yet after all this time. Kind of ridiculous, right? And you can see the frame rate is atrocious. And so the difference between compiling in debug mode and compiling in optimization mode when you have a situation like this where you're manually doing all of these operations to all the pixels on the screen all the time, debug versus non-debug makes a pretty tremendous difference, as you can see. So we'll have to take some steps probably to make sure that we put ourselves in a position where we can deal with that relatively well, meaning we'll have to start making some concessions that allow us to compile some stuff in optimized land as opposed to non-optimized land while not having to compile everything there. So what we'll probably do is split our build into 2 files for the handmade.cpp. One of the files will be the renderer pixel routines, which will get optimizations turned on, and the rest won't have it turned on in our normal build so that we can still have debugging everywhere else, if that makes sense. It's kind of annoying, but unfortunately, the Pragma optimize directives don't seem to usually give you what you need to turn on heavy optimization in just one little chunk. And so there's really not a lot of ways to deal with that other than splitting out the optimized routines into one file. But anyway, so let's take a look at that again, just to sort of wrap that up. So what we're doing here, right, is in our draw rectangle slowly, we're assuming now that we've stored our values pre-multiplied by the alpha value, right? But we've pre-multiplied it in linear space and then converted it back to sRGB. So this conversion is converting a value that's already in pre-multiplied alpha that's been baked into sRGB back into linear, where we can do our lerps with pre-multiplied alpha in there, right? We then do all of our stuff and then we store it back still pre-multiplied, right? Although it looks like, correct me if I'm wrong here, but we took care of, no, we didn't, so that's fine. The RGB still got to be multiplied there, right? The color A we took care of out here, but we didn't take care of the rest of it, right? So that's all fine. That pre-multiply is fine. We could also save a little work here. If you think about it, we really could just have pre-multiplied color first, and then just done the straight ahead multiply, right? That's something to think about. Like, for example, this right here could just be this. That would allow us to not have to do that extra multiply of the A every time, because what we would do is we'd just out here, we'd take color and pre-multiply it first, right? So we'd do like pre-multiply color up front. And so we'd just do that, right? And so probably worth doing, in my opinion. Because if you pre-multiply the color up front, then that means that you save one multiply by the alpha every time, because now you just multiply by the R, which already has color A multiplied in, and so you don't have to both multiply by the A and by the R. So that just sets us up for, you know, a better time when we actually go to do the optimization there. So that seems reasonable, right? Okay. So yeah, that's all seems pretty good. We have about 20 minutes left. I'm not sure I want to start doing the thing that I was going to do just because it took a bunch of time kind of going through that premultiplied alpha stuff. But yeah, so let's just continue down here. So we grab our values at, which now are already premultiplied. When we do our conversion up, we do our lerps, which should work because we're in premultiplied space. Hopefully, that's the goal anyway. We then multiply by our modulation color, which is basically the color that we use to tint things here, like RGB values that we might want to change, and the alpha value, which allows us to change how transparent this thing is as a whole. We read out whatever is in the current destination, and we assume that that was in sRGB as well, because we are going to store it that way. So we convert that up. We compute the inverse of the alpha that's now had both the texels alpha and the colors alpha multiplied together in there. We do the blend in linear space, right? We then convert from our linear space pre-multiplied back into the frame buffer, and we output, right? So I believe that is a pretty correct math pipeline. But I could be missing something still, right? So if there is somebody out there who's a serious render fellow who sees anything missing, I would highly appreciate you taking the time to let us know, but that seems roughly right. Seems roughly right. And like I said, one of the big problems with stuff like this is, it would be nice if we could just run it and see when it was wrong. But we're not going to really have that. Only really gross errors are often going to show up that way. And so what we could do down the line when we're kind of done with the renderer stuff a little bit is we could make some tests. If we can think of any good tests to do that would sort of try to suss out any places where we may be doing our conversions wrong, that might be something we could look at. Right? All right. So let's just do a little bit of cleanup then. Since we have 15 minutes to go, I think probably rather than start something new, what I'd like to do is just clean up a few things. So if you remember correctly, in our render group, right, I had said remove the header. And removing the header is a good idea, I think. Removing the header is something we should probably do. So if you remember, the way we were doing this is we had a buffer where we would put in all of the things that we wanted to send to the renderer, but each one of them had to have this render group entry header thing. And that's a little error prone, and there's really no reason to do it. I just kind of did it because we were, that was how it shook out when we typed it, but we don't really need that. Because what we can do instead is we can just have our stream encode and decode here. When we push things onto the buffer and when we pull them off, we can just have that know that it looks for a type first, right? Really, really straightforward. So what I would suggest that we do is, again, we go ahead and do that. So we take a look in here where we're actually pushing stuff on, first of all, when we push render elements on there. And all we have to do is say whatever the size is that the person's trying to push on, let's just go ahead and increase that size by however big the header is, right? That way, when we push it on there, we will sort of get the header, right, first, and then we will also get space for the rest of the thing, right? And so we can go ahead and set the header and set its type in the buffer. And again, I'm just doing, right, I'm just saying, well, we've got sort of this buffer here, right? And what we were doing before is we were pushing something onto it, right, that say took this much size. And we knew that the first thing of it was this header, right? And so we would return it, and then the caller would go, oh, okay, thanks for this header piece. I'm going to set that in the thing, right? It was looking at this guy. And what I'm saying now is, well, let's just talk about it in terms of doing two sequential pushes. So when we push it, first we push the header on, and then we push the data on, and then the data people never have to care about the fact that there was a header at all, right? So the header is just in there as a little sort of thing that the stream control uses to understand what the structure looks like, right? So here we go. We push on the size of what the person wanted plus the header. We then say, okay, make sure we've got enough room for it. Assuming we do, now we find out where the header is by looking at where the push buffer base is. We go ahead and set that type, and then we take the result. What we're going to return is just going to be the header plus 1, right? It's just going to be one, like the next byte after the header is full size. Because remember, in C, it'll do the pointer arithmetic for us if we have a sized pointer. So header plus 1 is whatever the byte location is of header plus the size of the header, right? And so, we end up, again, in that situation. To make that a little clearer, though, I could also alternatively write it this way, so you can see, right? If I do this, that's saying, like, okay, take whatever header is and move however many bytes header is size-wise, right? And off you go. So then the header's type is set correctly. These guys all get back the correct thing. So all we would have to fix then, I think, is this part right here, which is after we grab that header out, right, what we want to do is instead of these guys then casting using that header as a cast there, which is not what we want to do, right? What we'd rather do is have them just kind of look at the data, which will prepare the pointer for them to point to the correct place, which is right after the header, right? And so what we'll do is we read the header out, and then we say, okay, after the header, we've also got a data pointer, and that is literally exactly the same thing that it was before, right? Like so. So there's our data pointer. There we go. And what does this want to do? Oh, this is returning a render group entry header. That is not what it should return. It should return a void star, because now it is not returning the header, it's returning that data pointer. And so we should probably step through that and make sure it works, but we could just say, let's go for it. No, okay, of course not. So let's go ahead and step through that and take a look at how that's actually working and debug it. So I believe the first thing we typically push on is a clear, right? So let's take a look at how the clear works. So we come in here and we have the size that the clear is actually going to take, right? This is the render entry clear, I guess, structure, which is 16. We want to add to it the size of the header, which is 4 bytes long. So there we go. We see if we can get that, and we can. So we then grab a pointer to the header, which is going to be the first thing in the buffer. We then set the type, which of course is still clear. It happened to already be 0, so it didn't really change it there. But then we want to make our result pointer. We want our result pointer to be 4 bytes after the header. So hopefully we should see that happen here, which is 5C, right? So that's what we wanted to see, because now we should be able to see char star result minus char star header should give us the size of the header, right? 4 bytes, which is good. Then we increment everything forward. So that's all good. And so I think that's probably working correctly. What I suspect is not working correctly now that I think about it is we didn't advance the pointer properly. So I kind of forgot about that. So when we do our base address plus equals size of entry here, we forgot I didn't actually increment our base address for having read the header, right? So the base address here just needs to be incremented to account for the header size. That's probably all that we did not do. So that's probably it. Again, that just cleans it up a little bit and makes it so that all the code that uses that doesn't have to be aware of any of that stuff, which is nice. And man, yeah, we've sure slowed down our bitmap drawing. But what are you going to do? We'll have to take some steps to speed that up pretty soon. Or we can just start compiling it with optimizations on. But when you start compiling with optimizations on, it makes it a lot harder to debug stuff. So that becomes a little bit of an issue. So anyway, especially for a stream where I'm trying to show things in the debugger, it makes it pretty hard because the instruction pointer tends to jump around and it's just a little more confusing. So anyway, that is in the entirety of that. Trying to think if there's anything else in particular that I wanted to clean up in here that's a small scale thing that doesn't introduce anything new. I don't know why we need that comment, is kind of useless. I think this is all fine here. I don't see anything else that needs to happen. We've got all of our debug code. We've got this. Yeah. So that's all good. So I think we're pretty good for right now. Trying to think of what else I might be able to do that wouldn't be, you know, sort of starting something that we can't really get at all into. We don't really have much on the list here that isn't something that we would have to start. I guess what I could do is start doing that pullout so that we can compile those routines. Like what I could do is say, all right, there's handmade optimized.cpp or something like this, you know, something, I don't know, where we are going to stick routines like this one, like so. And we could do that. Of course, it's kind of a little nasty because it's hard for these guys to properly see all the rest of the things that we want them to see. So typically you don't really want to do this pullout with the optimizations until you actually have these optimized in sort of a at more of an assembly level, because you run into the situation where, like, okay, if I want to still use Unity build and I want to pull these out so that they get optimized separately, you know, I have to start segregating my inline functions that they might use, right, and other things like that, which is just kind of annoying, and I don't really like to do it. So maybe that's not the best idea. I'm not sure. What to give you a little bit of perspective on why this is a problem, right? There is a way, if I wanted to, I guess this is probably what I could do with the rest of the stream. Let me not introduce that file just yet. There we go. Okay, so let me delete handmade optimized before I go down that path. So the optimization pragma, right? I'll show you a couple different things here. So there is in Visual Studio, in Visual C++ in the compiler, there is a way to bracket things with some optimization directives, right? So you can say optimization list on and off, and there's like global optimizations, shorter, fast sequence machine code, blah, 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 right? But I don't actually know if it will fully optimize stuff to the extent that we would want it to just by using these with on. I know with off you can shut off a lot of things, but I don't know if on will actually turn on all the stuff that we might want. We could try, but I don't actually know, right? And furthermore, I'm not sure how you can push. So I guess when you use the, so if you take a look at what this even says here, it suggests that it won't do that at all, right? When you use the on parameter, it resets the optimizations to those you have specified with the /o compiler option, right? But oh, well, okay, but that's only if the string is null. So maybe this will work. Maybe this will work. If we can get away with it, it would be nice. Let's try it. Who knows? Because if we could do that, that'd be nice. Then we wouldn't have to ever worry about splitting the stuff out. Although we may eventually want to do that anyway, but that's kind of a separate issue. So let's see if we can get this to actually optimize by just telling it to turn on everything, right? So if I want to, I'm not optimistic, I will tell you that, but we'll give it a shot. So if I tell it I want to optimize this routine, and we'll say global optimizations on. I guess, do we have anything else? There's can be 0 more other pounds. So global optimizations, I think, is the only thing. Shorter fast sequences machine code. So I guess I want fast sequences of machine code for now. And yeah. And so then after we're done with that, after draw rectangle slowly, I just want to put in a pragma that says also you can, well, I guess I want it sort of around both this and draw bitmap. So let me grab draw bitmap and stick that in there as well. So it said that if I used it with nothing, it would just revert to the old optimization settings. So I don't know if that actually optimized. I'm doubting it did. And it certainly doesn't look like it, right? This is nowhere near the speed that we were getting before. So yeah, that really does not seem to do what we needed to do, right? As far as I can tell anyway. We got pragma optimized GT on, and it really didn't optimize our draw bitmap into anything noteworthy. I could double check, right? Like turn on Visual C optimizer for just one function and see if anybody has any information about that. Let's see here. Optimization, floating point switches. Optimization decal specs, no. So let's pull this out a little bit so we can read it. So let's see. On a function base, the ideal for those variables created when a given function is compiled with optimization. Okay, that's not what we really wanted to hear. What we want to do is just set one of them to be on. For more, let's see. Yeah, this is not helpful. Because most of the time they're thinking disable optimizations, but what we want to do is enable optimizations. I guess we could wrap everything else in a pragma optimize off, but that doesn't seem like such a good idea. I don't know, but maybe we could try it. This is something I've never done before, so I don't know. Maybe we'll try it. If wrapping just that in a pragma optimize on doesn't work, maybe wrapping everything else in a pragma optimize off would. And so maybe we do this, right? So we say pragma on, pragma off, like so. And then we literally, in our handmade.cpp, at the very top of the file, we turn all the optimizations off. And then at the bottom of the file, well, at the bottom of the file, we don't have to do anything. What will that do? I don't know. So off the bat, it should do nothing because we don't have any optimizations enabled, so we're in slow mode, and so that's fine. But then if I go into our build and turn optimizations on, what happens? I have no idea. Still totally unoptimized, it would appear, right? Like, that's not at all helping us. Yeah. I feel like that should have worked, though, right? So I wonder if there's more to it. I wonder if it's because inline functions that, like perhaps inline functions can't be optimized if they're in the optimize off or whatever. I'm not sure. But for whatever reason, it looks like we're not going to be able to do that. So we'll give up. It's not absolutely essential. What it means is we'll have to maybe do some optimization earlier rather than later so that we can still compile with optimizations off and be able to step through code and sort of show, do that illustrative stuff. Because the reason that I'm spending so much time dithering about this is because if I compile with optimizations on all the time, I just want to show you what it looks like when you sort of start stepping through. Do you see what's happening there? Do you see how it's jumping around like that? It's basically because the optimizer has rearranged all the code, and so it's very hard for me to sort of teach on the stream and show, oh, this happened and let's look at the values and all that stuff. If the IP is, jumping all around like that to execute the function, right? Normally you might just be fine with that, and that's not really a problem, so we just compile with optimizations on and we'd be done. But unfortunately, that's not probably realistic for Handmade Hero, so we will have to do something to sort of make sure that works out. And so maybe I will try to split those into two separate files and compile one with full optimizations, and we'll just pull out the sorts of stuff that get needed into handmade optimizations.h. Like we'd have handmade optimizations, optimize.h or whatever, and that would have the inline functions that we expect to have in there. And then we'd have the other one as well, or something like that. So you can envision it working relatively cleanly. So maybe we'll just go ahead and say that that's what we're going to have to do. Maybe I'll do that tomorrow, for example, and that'll be our thing. All right. So let's take a look at the Q&A because we're about out of time here. So let's go ahead and go to the Q&A. If you do have if you do have questions, please prefix them with Q:, starting now, and I will take a look at them. Yeah. I really wish there was a way for Visual Studio we could just say, optimize this function extremely heavily. Just this function. Because that would be all we really want here, right? And I've encountered that on my own code base as well. I prefer to compile in debug mode most of the time because it just makes it easier to view things in the debugger. And so I would really like to be able to say, hey, this is a critical function. Just optimize this one, please. Would be pretty awesome, right? So, yeah. So anyway, does anyone have any questions? Arbsfeld, why can't you compile OpenGL code to C to make a software renderer? I don't think I understand the question you are asking. What is OpenGL code in this case? Mr. Fourth Dimension, is it useful to be able to debug with optimizations on? Do you think you might be able to show how to do that at some point? So the first thing you need to do is if you want to debug with optimizations on, you're never going to really get around the fact that it jumps around like that. That's just the nature of the beast. But what you can do to make life a little easier on yourself is Visual Studio debug optimization switch. I don't remember what the switch is. It's in here. Oh, it might be that guy right there. Enhance optimize debugging. So I believe this is always off by default. And so I can try to give an example of why this is something you probably will want to know. So I'll just show what happens. So in our build.bat, right, we've got that O2 in there. So this is an optimized build. It's getting optimized fairly heavily by the compiler. If I come in here and start to try and do stuff, like let's say I try to see what min_x is, right? Well, min_x, according to it, is undefined. It has no idea what min_x is. Now, it's right there, right? But it has no idea what it is. So the reason for that is because the way that the compiler chose to optimize this code, there's no longer an easy way for it to look up what the value of min_x is, right? So it just doesn't show it to you. It's like, I don't know, right? I have no idea. And so if you wanted to know what min_x was, and you're in here, you'd actually have to go in, and you'd have to go to the disassembly, right? And you'd have to actually look to see where it had put it. Like, okay, it's being called from XMM, it's putting it into EBX, and then, so min_x should still be there, it looks like. So if I looked at where EBX was, which is here, this is what that is, right? Like, it's like, that's the process you'd be going through, which is really time inefficient and very error prone, right? So one of the things that they added that was a nice feature, I think, in 2013 compared to like 2012 or something. I don't know, that they added at one point. It was not something you could really do before, and they added it at one point. If we instead go in here and add that ZO switch, right? In theory, that creates a more extensive debug sort of annotation in the PDB file that goes with your executable. If you remember way back from the first days when we were looking at that stuff. More extensive annotations. So sometimes now when you go through here, the debugger can actually tell you. Unfortunately, it looks like in this case, still can't tell us, right? So not particularly useful, but at least it knows about it now, and is going to tell us that it's not available. But so sometimes you will get more for that. Like source offset is probably one you would not have gotten. For example, like you can see it now. It's 83. I'm going to go ahead and say, so let's say we can see that it's 83 here. I'm going to go ahead and say that probably that was one that if we took the ZO out, you probably wouldn't be able to see, right? That's just my guess. So you can see identifier source offset x is undefined. So, you know, it gives you something. It allows you to see a bunch of values that you wouldn't otherwise see, and that's very good. So minus ZO is something you probably want to add to the build. We probably should have added it way back in the day, but you know, just didn't think of it. So that helps, but that doesn't change the jumpy aroundness. And so there's nothing to tell. I mean, there's nothing about the debugging. It just means the code was rearranged for more optimal execution, right? And you know, or collapsed away, or all those sorts of things that might have happened during optimization. So you just have to get used to that and understand that you're only getting an approximation, and you have to kind of drop down to disassembly now and again. And this is kind of annoying, but this is a thing where it's not sure which address you're actually talking about for debugging. But you can usually do a reasonable job by just stepping and then getting back to the place where you're at. So you have to kind of look in here sometimes to figure out what's going on, which is kind of annoying. There's really no tricks to this. It's just hard to debug in optimized land. It's much harder to do that than in debug. So what I recommend doing by far is never debug in optimized mode if you can avoid it, right? Always try to debug in debug mode when you can, and only debug optimized code when you have to. So you know, that's what I'd say about that. But you know, when you are, it inevitably happens. Because you have a bug that only repros in optimized mode, or it takes too long to run in debug mode, so you have to run in optimized mode, whatever, then that minus ZO is a good thing to know. Let's see. GLSL. Okay, so you were talking about compiling GLSL code into a software to make the software renderer. So the answer is GLSL has nothing to do with rendering at all, really. GLSL is shading computations. So the actual entirety of the renderer is none of the renderer is actually in GLSL. Only the shading computations are in there. Now, granted, shading computations have now grown to encompass a lot of things that are render-esque, right? But the whole superstructure, the whole part of the renderer that decides what pixels get filled, right? And sort of so I guess what I should say is, let's not use the word renderer. GLSL is not a rasterizer, right? It does not have anything to do with figuring out what pixels to consider. All it does is it figures out what the outputs are and the inputs are to very well-defined shading pipelines that basically take buffers in and put buffers out. But there's no pixels involved anywhere in there, right? And so the superstructure around GLSL, which you don't see, that's all implemented on the card or in the driver, is the thing that actually determines what pixels are actually getting considered to ever run the GLSL code on those pixels, right? And so that's a very small part of our problem, because shading code on 2D game is very basic usually. There's really just not that much. Maybe you do some normal map lookups, you know, for lighting or something like this, or some other little things in there. But for the most part, all of software rendering tends to be in the rasterizer. It's figuring out what pixels to fill. That's the most of the 2D rasterizer part of things, right? And so GLSL doesn't really help us at all, right? We don't really have any, GLSL is just not really a useful thing. If we wanted to, and we for some reason had a bunch of GLSL code that we'd already written that talked about how we were going to do our shader computations, and we didn't feel like rewriting it in intrinsics in the compiler, we could write a thing that read GLSL and outputted intrinsics that we could then compile. That's certainly possible. It's not really much, it has really very little to do with the renderer for a 2D game. It's just a very uninteresting part of it, right? Whereas, you know, maybe in a 3D game, there's a lot more of it because maybe you've got tessellation shaders in there and geometry shaders in there and vertex shaders in there. And then the pixel shaders, which are much more complicated because they're doing all kinds of crazy stuff in terms of approximating things and post passes and all these sorts of things. So maybe, you know, that would make some sense if you're doing a software rendered 3D game. But even then, I just don't know that it buys you anything, because who cares? GLSL is just a programming language like any other one. Why not just write it in the actual language? There isn't any use for that in some sense. Now, if we were going to have a lot of shaders, one reason you might do that is because you don't want to have to rewrite all that code again when you do hardware, when you implement it in hardware, right? And so it's definitely true that if I thought we were going to have a ton of shaders, then that would be a case where we might want to go, all right, let's make sure that we can do this, have a common language that describes both. But the way to do that might still not be to actually look at GLSL code as a source language and compile it. What you might want to do is just make a little macro language that would expand to GLSL or to your own code and just do it that way. Like reading GLSL might not be worth your while to do, right? So I would just say that that's just not a very interesting part of this problem. We're not going to be spending a ton of time writing shaders because they're just not that useful in the kind of game we're talking about here, which is about putting a lot of bitmaps on the screen. We just won't probably have a ton of shader code. It's really the smallest part of the rendering process, and the rasterization is the big part. Should the load bitmap function also be optimized after making changes today to do premultiply? Yeah, I mean, probably not, because that'll probably just get rolled into whatever prepares our assets. So I'm thinking that that's probably not that useful. We don't load very many bitmaps currently, so it's probably not taking hardly any time. It's the ground chunk preparation and the screen blitting, I think, that are probably taking all of our time at the moment. How would something like a dynamic array in this memory system work? Something that is persistent across frames but able to change size. Holes are not possible in the memory arenas right now. So the answer to that is usually like, it depends on the circumstance. If you want a dynamic array, you can just do, you just have to put well, let me put it this way. If you end up wanting something that is totally dynamic, like a dynamic allocator, then you have to write a dynamic allocator. Like, that's what malloc and new and all those things are doing under the hood. They're taking large chunks of memory and apportioning them up. And what they do there is if they produce holes, they then later try to fill those holes with other allocations that are similarly sized, right? So if you really do end up wanting something that's totally dynamic, the whole system ends up being kind of totally dynamic, you need a dynamic allocator. And you could write one of those. They're not particularly hard, right? But I usually say, why do you need the dynamic array? Are you sure that that was the best idea, right? Because most of the time I find that dynamic arrays are not such a good idea. Usually you can write it in a way that's more predictable, because any dynamic array opens you up to the possibility of memory fragmentation, even if you have a dynamic allocator, and it also opens you up to other possibilities that aren't so nice, such as unpredictability in terms of when allocations happen. So I feel like I would say, be sure first of all that you really want dynamism in your memory allocation that way, because it's not always such a good thing. Couldn't a compiler translate the OpenGL commands to C commands and wrap them in a loop which iterates over the pixels? Well, sure, it can, but take a look. I mean, let me try to, if you were not convinced by my explanation, let me show you just literally the code that we wrote. Here's draw rectangle slowly, which is most of what we've done so far in terms of rendering, right? Here is all the code to draw the texture map rectangle, right? The part of it that is the shader is right here. So this is 4 multiplies that you would have implemented an entire GLSL pipeline to get. The rest of this is the blend output, so that wouldn't be there, right? Because the blends are not programmable in GLSL at the moment anyway. Although I feel like someday that's probably going to happen. But right now the blend unit is not a fully programmable unit, so this is not in GLSL, right? This is in the texture unit, so this is not in GLSL, right? I mean, maybe if you were, if you call, there would be one GLSL line called texture or something that had to do, and it would expand to all of this stuff, right? this entire part here. That's all in the texture unit. It's not in GLSL, right? This is in the texture unit. It is not in GLSL. All of this is the selecting of the pixels, not in GLSL, right? So the code that would be in GLSL is literally that. Like, that's the part that you would be saving. And I don't see why you would bother, right? It just doesn't make any sense. Because this is the shader for this effect, which is just tinted thing. And so, yeah, will there be a little bit more later? Probably there'll be like a normal map thing or something in there or whatever. Like, we'll have a little bit more. But it's just such a minute part. Why would you complicate your code by introducing this whole other language, this whole other translation process? Like, why would you do that, right? It's just a really bad decision until you know you're going to have tons and tons of code in GLSL that you need to translate that way, right? And I just don't see that being logical. Lucas Perrin, could you explain us how you free all the memory stack when closing the game? You don't. Windows, all modern operating systems discard 100% of your memory when you close, so you don't have to free any of it. I have a hard time understanding why sRGB conversions are required for the alpha channel at all. Well, so first of all, they're not happening in the alpha channel. So if you notice, sRGB conversions are not happening in the alpha channel. We leave the alpha channel unconverted. It's linear. And why your initial code wasn't correct. The alpha channel is being used to represent a proportion of photons from one source and a proportion of photons from another source. Wouldn't that be outside of the purview of color curves because it doesn't technically have anything to do with brightness? Yeah, so you are correct in your intuition. The alpha is not an sRGB value in our current system. We are not converting it. You seem to be manipulating colors on a low level. How are you pushing pixels? Sorry, I'm kind of new. You want to go back and take a look at the video archive. So on handmadehero.org, actually, if you go to the forum site, is probably the best place to go. So if you go to forums.handmadehero.org up there, what you can do is you can go to the episode guide. And if you take a look at the episode guide, there's sound and input on Windows, simple frame buffer on Windows. So week 1, this is what you want to watch. That'll tell you. Any reason you write texel A plus dest A minus texel A times dest A instead of just inv star dest A times texel A, which would match everybody? You know, no, there isn't. It's actually just because I worked out the math on the blackboard, and this is what it worked out to, if I remember correctly. So yeah, we can do that. If you take a look at what he was suggesting there. So if I rearrange this, so I move this, so just so you can see. So here's texel A, right? If I move texel A to the end, so keep the exact same equation, then what I can do here is this is just 1 minus texel A times dest A, which is inv RSA, right? So, you know, we could just write that much more concisely there. I had just copied it down from the blackboard, but that is, yeah, definitely, it makes perfect sense why you would want to do that. It makes it much cleaner and more, definitely easier to read, right? The other thing we could do is recognize that because we've gotten this down to such a straightforward thing now, if we want to, we can also say, well, this is just inv RSA times dest plus texel, right? That's all that was. So now it's a little cleaner to read as well, I suppose, right? So that's always good. We can just keep on keeping on, right? Condense and condense and condense. And so that's kind of fun. This also is obviously the Hadamard product. So we could actually call texel equals Hadamard texel times color, right? Oops, not plus. texel equals Hadamard times color, right? And that's the same. I should double check, obviously, that the, let's see, should double check that our crazy psychedelic thing works still. There we go. Lovely, isn't it? So yeah, so that can all be condensed quite a bit, obviously, and possibly should be. Similarly, we could do this guy down here because it does the exact same code, right? This is the same rearrangement, right? So move the texel to the end, like so, and then recognize that this is just 1 minus texel A times dA, which is invar SA, right? And then that collapses. It's the exact same operation. So result is just invar SA times D plus texel. And that is, of course, the only place where invar SA is used. So you could substitute it in like so. So yeah, it just, you know, makes things a little bit cleaner, certainly. Wasn't the alpha channel authored with non-linear colors? So I don't think so, because the alpha channel is typically authored by Photoshop by writing the coverage value into each pixel when you paint with the brushstrokes. So I'm assuming, and I don't know this definitively because I don't have the source code to Photoshop, but I'm assuming that the alpha is not sRGB encoded. All right, so I think that's about it, seems like. No further questions, so I will call it a day. All right. Okay. In that case, let's go ahead and close these guys and save our Blackboard, like so. There we go. All right. Okay, that brings us to the end of another episode of Handmade Hero. Thank you very much, everyone, for joining me. It's been a pleasure coding with you, as always. If you would like to follow along at home, you can pre-order the game on handmadehero.org, and it comes with the source code that you can download every night so that you can sort of tinker around with it and experiment with some of the things that we're doing. So that's a really good way to learn if you want to give that a shot. We also have a Patreon page. If you want to support the video series, you can subscribe to that. And we have a forum site which you can go to, where if you go to the forum site, there's a bunch of cool stuff. There's an episode guide, there's code discussion, and there's a ports to Mac and Linux, all kinds of good stuff there. And there's a tweet bot that lets you know the schedule. I highly recommend checking out the tweet bot if you are interested in catching the stream live, because it always tweets the schedule at you, so you can always kind of know when it's going to be live. So that's a good way to do it too. So tomorrow we'll sort of pick up, I guess maybe we'll start thinking about how we're going to keep things optimized relatively well while we go forward. Maybe separate some of that code out, do whatever needs to get done there. And then we'll sort of push forward on our renderer, since I think we're in pretty good shape here. We cleaned up some stuff today, and we can maybe start adding some stuff tomorrow, so that'll be good. So yeah, hope to see you tomorrow. Same time, same place tomorrow, 5 p.m. Pacific Standard Time, right here on Twitch. So hopefully we'll see you for that, and have a good Wednesday. Until then, take it easy, everyone.